Hello everyone, let's go ahead and take a look at continuity, which is an application of limits. Now if you go back, so let's say for example, maybe about 8th grade or maybe 9th grade, and you first started talking about functions. It was at that time probably when the word continuity actually first appeared. And when that term was first introduced, usually it was in this context. Is this function, for example, continuous? Now, in order for us to go ahead and determine that from a very qualitative standpoint, basically what your teacher probably said something along these lines. If you start from this side, and you were to trace the function with your finger or your pen, if you were able to do so, going all the way from left to right, without having to lift your pen or lift your finger off of the paper, then the function was continuous. If, say for example, like in this case, if I was to continue this way, if I indeed lifted my finger off of the paper to actually go ahead and start the function again at a different location, or even in this case over here, lift it to move over here, come down here, and come back up there. Since I'm lifting my finger off of the paper, I've got what is called a point of discontinuity. Okay, but of course we want to move way beyond that. And we want to take a look at how we can apply limits to actually define continuity. Now, in order for a function to be continuous at a point, 3 conditions must be satisfied. Okay, f of c must exist, in other words, the function has to exist at that point. The limit as x approaches c of f of x must exist. And remember we said that these two things don't necessarily have to mean the same thing. If, as well as these two, the limit as x approaches c of f of x is equal to the function's value at c, then you know that the function is indeed continuous at that point. So what I have up here in this graph is that I've set up certain situations. And what I have here is I'm going to focus on the x value c sub 1 through c sub 4, and we'll take a look at what exactly is happening to this function to determine whether at that point the function is continuous or not. Okay, so let's take a look at c sub 1 first. If I go ahead and take a look at c sub 1, is f of c sub 1, does it exist? And if I go up here, and if I was to just go up here, sure enough, the function's value f of c sub 1 exists. So this is a yes. Okay? Does the limit exist? Well, the limiting value, if I approach c sub 1 from both the left and the right, of course the functional value is going to approach this exact value there. So sure enough, the limit exists as well. Now, does the limit as x approaches c of f of x equal f of c? And sure enough, when I take a look at this, the limiting value and the actual value of the function are coinciding. So therefore, I know that this is a yes as well. So is it continuous at c sub 1? And the answer, of course, in this case is yes. Now let's go ahead and take a look at the c sub 2. Does f of c sub 2 exist? Well, here's c sub 2. Does f of c sub 2 exist? Sure enough, it is. It does. It's right there. So in this particular case, again, it's yes. Does the limit exist as x approaches c? Well, the thing about the c sub 2, well, the thing about this is that as I approach c sub 2 from both the left and the right hand side, the function's values are not approaching the same values. So what I know in this case is that's no. Now, once you go about proving any one of these 3 not true, then you can automatically deduce that the function is not continuous at that point. So c sub 2, is the function continuous at c sub 2? The answer is no. Let's go ahead and take a look at c sub 3. C sub 3 says f of c sub 3 must exist. Does it exist? And the answer is no. It doesn't exist. Okay, and so once we have that, then we know, of course, that this is a no. Now, let's go ahead and take a look at c sub 4. Does f of c sub 4 exist? And sure enough, it does. It exists. It's right there. So this value right over here is a yes. Now, does the limit as f of c, does the limit as x approaches c sub 4 of f of x exist? And sure enough, as we approach c sub 4 from both the left and the right hand side, the function is approaching the exact same value, and that little t value is there. So the answer for this is yes. Now, does the limit as x approaches f of c, does the limit as x approaches c sub 4 of f of x equal to f of c sub 4? And of course, the limiting value is up here, but the actual value of the function is there. So therefore, this is a no. And therefore, we can say that this is a no as well. So notice that in this particular situation here, the only place where we have continuity at the particular point that we're investigating is at c sub 1. Okay. Now, the other thing that we also need to go ahead and determine is whether or not, if we do have a point of discontinuity, so for example at c sub 2, c sub 3, and c sub 4, is that point of discontinuity removable or is it non-removable? Now, when we go ahead and go back, again, let's think about our qualitative example when we were back in grade 8 or grade 9. How can you tell if it's removable or not removable? Well, the thing is, here's one of our points of discontinuity, here's another one, here's another one. Is there a way for me to go ahead and make the function continuous just by adding a single point? So in this case, of course, there's this huge gap that I have to bridge. So that means that for this particular c sub 2, there is no way that I can put one point in there to make the function then continuous. So therefore, I call c sub 2 non-removable. So this is non-removable. Now let's go ahead and take a look at c sub 3. If I take a look at c sub 3, if I put a point in there, all of a sudden the function now is continuous. Because now f of c exists, the limit exists, and they are both the same value. So what I call this particular point of discontinuity is irremovable. Now what about c sub 4? C sub 4 is kind of an interesting case. Because of course we already have a point there. And if we put a point there, then we no longer have a function, because now, of course, it doesn't pass the vertical line test. But of course, all we're trying to do right now is think about whether or not we can actually make the function continuous by adding a single point. And notice that the only part that was actually having trouble here was this part right over here, because that was the only thing that was creating the discontinuity. So in other words, if I actually go ahead and put the point there, then I will then go ahead and have a removable point of discontinuity. Okay, now let's go ahead and take a look at another example here. Because of course one of the things that we want to do is we want to actually talk about specific functions and make sure that we can approach it from a algebraic perspective as well. Now the one thing that we have here, here's our graph, is that we have a vertical asymptote. And we know that for the vertical asymptote, its x cannot be equal to 0. Now, if I was to go ahead and consider this to be our c value, which is 0, let's go ahead and determine whether that is a point of discontinuity or not. Is the function continuous at x is equal to c? Now, if I go ahead and say, does the limit exist? Of course, the answer for the example is no. And therefore, we know that it is not continuous at that point. Okay, which is of course what a vertical asymptote is. Now the thing about this, let's just continue with some of these. Does the limit exist? Well, the limit, of course, is actually going to be equal to infinity. But we said that the limit doesn't exist when you actually have that. But we just be more specific about what it's approaching. Now, the limit as x approaches f of x, the limit as x approaches c, which in this case is 0. Oh, I'm sorry, just put 0 there. Okay. So the limit as x approaches 0 of f of x does that equal to f of 0, and of course that answer is no as well. But the interesting thing about this, and the reason why I put this particular example on there, is of course it's going to get closer and closer. We always say that it's getting closer and closer and closer and closer to the vertical asymptote. shouldn't there be a point where you can just put one point on the vertical axis, or sorry, yes, on the vertical axis or the y-axis, so that then you would actually join the two parts of the function. And conceptually, when you think about things visually, it would seem to make sense that you would actually be able to find that point or that position all the way on the y-axis, so far up there, that you'd be able to put that one point there and it would be continuous. But in fact, it never will. And there's never going to be a place on the y-axis where you can put one point on the y-axis that would then go ahead and join this left-hand branch and that right-hand branch. So that's just something to consider there. Okay, let's just wrap up again. So in order for us to go ahead and have a function be continuous, again, these three conditions all must be satisfied to go ahead and be able to say that the function is continuous at that particular point. So we'll go ahead and take a look at any questions that you might have in class the next time that we meet. See you then. Bye-bye.